Okay, so we'll start with our today's lecture. The first thing that we are going to discuss today is time and space complexity. That's sorry, time and space complexity. So these both complexities always depend on the input and the type of code you have written in a particular case. So every time whatever the input you give, if the complexity of particular code, how complexity of a particular code will vary, this is what we known as time complexity, and how the particular space will vary is known as space complexity according to the input. Okay, so let's say I'll write a function. um, that's a void function n that takes an integer n. Let's say what this does is, for int I is equals to 0, I is less than 100, I plus plus. It is just printing something. Can you reduce the complexity for this in the terms of big O? Okay, it's not n for this case, it's O of 1. Let me tell you why. Okay, so this loop started with 0 and ended at 99. It will not loop for the 100. So it is looping 100 times, right? So let's say you input n as 5. How many times this loop will repeat? 100 times. Let's say you input n as 10. This loop will continue for 100 times only. And let's say you have given some 10 power 8. Still, this loop will run 100 times only. So it is taking some constant time for any kind of input you are giving. So that's why it is a constant time complexity for this. So now in the case of n, what you were saying, let's replace this 100 by n. Now if I give n as 5, this loop will repeat 5 times. If I give as 10, this loop will repeat 10 times. If 10 power 8, then this loop will repeat 10 power 8 times. So it is taking variable time linearly proportional to what we are giving in our input. So this, now when we have replaced 100 by n, this complexity is O of n. Okay, so let's say we again write a function. Void function of int n. What it does is, for int I is equals to 0 to I is less than n, I plus plus. In this we are having a inner for loop with, for int I is equals to 0 to I, let's say, is less than 10, I plus plus. Again there are some print statement. So what will be the complexity of this? Yes, cool. So when this is repeating n times, this has a constant time complexity. So While denoting it as O of n to O of 1, we will just directly write it as O of n. We will ignore the lower order terms. This is how we write the complexity. We do ignore the lower order complexities. Okay, let's say I will tell you to why we ignore this lower order complexity. Let's say I have a code saying I have a function that takes some integer, and what it does is that it has a outer for loop that goes from 0 to n. Now in this for loop there is again a for loop of 0 to n. Okay, they are doing some operations. Now after this both of for loops, there is again a for loop that says I'll go from 0 to n. So now the complexity for these for loops is O of n square, because for every n this is repeating n times, and the complexity for this is O of n. So let's say the total complexity will be O of n square plus n, right? Okay, so let's say assume that our n is 10 power 4. Anything, we'll assume it to be 10 power 4. So this is 10 power 4, that is my n. So now in this is 10 power 8 plus 10 power 4, right? These will be the number of iterations we were having. Number of iterations for 10 power 4 n. For 10 power 4 input, this is the number of iterations we are having. So let's say we will deduce that how much 10 power 4 contributes to 10 power 8. It is just calculated, it is just 0.02%. So now this is really negligible. That's why we ignore the lower order terms. So I'll say that the total complexity for this function is O of n square. This negligible ratio is the reason to why we neglect the lower order terms. You got this point? Okay, I'll take the new one. So what I was saying is that I have a function int n. What it is having is a for loop that goes from 0 to n, and in this for loop there is a for loop that goes from 0 to n. Some functions it is doing, some statements that will take O of 1, some print statements or something. Okay, so now again I have a for loop that will go from 0 to n. So the complexity for this for loop is O of n square. Is that correct? Okay. The complexity for this for loop is O of n. Is that correct? Okay, so I can say that the total complexity will be n square plus n. So now let's assume I give n as 10 power 4. I assume this thing. Now let us find out the total number of iterations we will be having for 10 power 4 n. That will be equal to n square plus n, that's 10 power 8 plus 10 power 4. Now let's say we will find out that what is the ratio of 10 power 4 and 10 power 8. 10 power 4 is just 0.02% of 10 power 8. Calculate this thing, you will get the 0.02, the percentage of 10 power 4 in 10 power 8. So this is really negligible, 0.02%. Is that negligible, right? Okay, so that's why while writing out the complexity, what we say is that if there is any negligible value like this, we will neglect that and we will only have this particular higher order term. So I'll say that in total, the complexity is O of n square, not O of n square plus n, just n square. Got this point? Okay, note this down. Okay, so we'll go for the next question. Um, let's say I have a void function that takes some integer, and what it does is um, it goes from 0 to I less than n, I minus minus. What will be the complexity for this code? Um, can you find me the complexity for this code? Okay, that's an infinite loop. This is having an infinite complexity. Okay, so we'll proceed to the further questions. Okay, so let's say for int I is equals to 0 to I is less than n, I plus plus, inside if it is having int j is equals to 0 to j is less than n, j plus plus, what we say is that it is an n square approach, right? So let's say I remove this and I put out, rather than 0, I put out I. What will be the complexity? Can you try to reduce it? Okay, let's say let's will just count out the number of loops we are having. Okay, so uh, I is going from 0 to n and j is going from I to n. What I'll say is that let's say here is my I, here is my j, and here is my total count. Let's say my I is 0. My j will go from 0 to n. In this case, for this particular 0, the total number of iterations were n. Is that correct? For I is equals to 1, my j will go from 1 to n. and the total number of iterations for this particular one is n minus 1. Similarly, if my I is 2, my j will go from 2 to n, having total number of iterations for I is equals to 2 to be n minus 2. Similarly, going down, what I can say is that it will go to n minus 1. For n minus 1, when I is equals to n minus 1, it will go from n minus 1 to n minus 1, and that is equal to just one iteration. So I can say that the complexity will be equal to the sum of this column, because this is the total number of iterations we were having, total iterations. So this what it is, this is the sum of n natural numbers, right, from 1 to n. This is just a sum of first n natural numbers. So it's like n plus 1 by 2, that is n square by 2 plus n by 2. That's the formula for the sum of n natural numbers. So now, when I have already told you that we will ignore the lower term complexities, we will ignore this n by 2, and also we will remove any of the constants we have. So the complexity will remain O of n square. Okay, let's say um, we have a loop that goes from I is equals to 0 to I is less than n. What I'll say is that I is incrementing with the multiplication factor of 2. That's what I am having. So let's try to reduce the complexity for this. What I'll say is that here is my I value and here is my loop count, the total number of iterations I'll be having. So let's say my I is 0. My total loop count is till now 1. Sorry, we will start from 1, because this will fall into 0 category again and again. So let's say I've started the I with 1. The loop count is currently 1. I'll multiply the I with 2. The loop count remains 2. Now I will increment to 4. The total loop count is 3. This will go to 8. The total loop count goes to 4. That's 16. And that 5. So for any number, this is the loop count we are having. What is this series according to this? This is a series of log. So I can say that for any given n, the complexity is equals to its log value. I'll say that the complexity for this is log n. Okay, so we will we will say that whether for this particular case, we'll try to deduce that whether big O is always correct or not. So sometimes big O is not always correct. So let's say I have one solution, solution 1, and I have again a solution 2. These both solutions are for the same problem. Let's say the complexity for solution 1 is 3n square plus 4n plus 10,000. So the complexity, the big O complexity notation will be n square. as we will remove all of the lower order terms and the constants we are having. Let's say my solution 2 is having n cube plus 1000. So according to this, big O will go up to n cube. So now clearly when we see big O of the solution 1 and big O of the solution 2, big O says that solution 2 is more optimal than solution 3, as it is going to n square and it is going to n cube. Let's say for the smaller values of n, let's say we will take n as 2. We'll count out the total number of iterations it's having. That's 12 plus 8 plus 10,000. That is something 10,020. This is for solution 1, the total number of iterations. For solution 2, our n is 2, right? It's 2 cube plus 1000. It's 8 plus 1000. That's equal to 1008 iterations. So for lower and smaller values of n, the solution 2 is working more optimally than solution 1, as it will be having, for let's say for 2, it will be having 1000 iterations around, and this will be having some 10,000 iterations around. So big O is not always correct. Big O is all correct only when we have crossed a certain threshold value. So we will not consider these smaller values in the big O notations. So what big O says that big O puts a upper bound for the time required for a solution after a certain threshold is achieved. So let's say we'll again have two solutions, solution 1 and solution 2. These both solutions are for the same problem. Let's say my first solution is some 3n square plus 10, and my second solution is n square plus 30. So the big O notation in this case will be n square. Again, the big O notation will be n square. So now, according to the big O notations, both of these are similar, but still it will be having 3 more times of the iteration to this solution we are having. According to the big O notation, these both solutions are having the equal time complexities, but in reality it will be not. Okay, so we will discuss now the amortized complexity. So generally we have big O, theta and omega, right? There is also amortized complexity we have. This now where we get this amortized complexity into the picture. Amortized complexity comes into the picture when we are having a certain function that occurs very rarely, but it has a very high complexity. It's very rare, but it's very expensive. So let's say I'll take an example of array list. So at first, the array list will be created of 16 elements, right? Now let's say I fill up this particular cell. Again, I fill up this particular index. I fill up this particular index. For filling up this index, it's O of 1. Insertion operation in an array list. Again, it's O of 1. Again, for this, it's O of 1. Similarly, for this, it's O of 1. Let's say I come here where it is maybe the 12th index, something as the golden ratio is 0.75, the fill ratio. If you don't know what fill ratio is, go and read about what fill ratio is for array list. So let's say I'm at 12th index. The insertion operation for this will be including a creation of a 32 elements of array list. That's 32 elements array list, copying everything from here to here, every of the element, and then inserting the particular element to this particular position. This is how it works. So let's say for this the complexity was O of 1. Again for the second one it is O of 1. For the third one it's O of 1. But for the 12th one, what I have to do is to create an array. Then the number of elements we are having, the n elements, we have to copy them. So for the insertion at 12th index for this particular array list, the insertion operation cost us O of n because we have to copy all of these elements below. So this particular operation is expensive when it is compared to this, but it is very rare. That's very rare. So according to the amortized complexity, what I'll say is that to neglect the rare cases we are having in a particular code. So what I'll say is, just a second. What I'll say is that I'll ignore this, and what I'll say is that insertion operation in an array list is always O of 1. Okay, so we have done a lot of questions on time complexities. Space complexity is also a bit similar. So let's say we will try to deduce the space complexity for a particular question. Let's say I have a function void function of int n. What it does is to create an array, int array, that is a 1D array, new int of n. Let's take 10 first. So now, just a second, I'll erase. That's 10. So let's say we give our input n as 5. The array size will be 10. If we give 10, the array size will remain 10. And if we give some 10 power 4 element or some 10 power 8 or whatever we give, the array size will always remain 10. So this is some constant space. So what I'll say is that space complexity is O of 1 as it is always constant. So now let's say rather than creating a 10 array, I'm saying that I have created a new int of n. So now whatever the value of n I'll give, that will be directly proportional to the space I'm using in the code. Let's say I have given n as 5, the array size will increase to 5. If I have given the n to 10, my the space I will be using in this particular array will be 10. Let's say I'm giving 10 power 4, then the array created will be of 10 power 4. So what I'll say is that the space complexity for this code is O of n, that's linear. Let's suppose rather than creating a 1D array, I created a 2D array. So now the space complexity will be O of n square. Note this down. Okay, so we'll proceed. So now we will discuss a bit of recursion and then we'll try to find out how we can deduce the complexity for recursive solutions. Till now, all we did is everything was iterative approach. Let's say everything was a for loop. Again, this was an iterative approach. Everything till now was an iterative approach. So now, let's say we will discuss the bit of recursion, and as soon as we are comfortable with the recursion, we will try to find out how we can deduce the complexity for a recursive solution. So first of all, what recursion is? Can you tell me what is recursion? Yes, a function calling itself. Yes, that's a very well-known thing. Okay, so let's put it in some other words. A function is calling itself. Why will a function call itself? And we will try to deduce the answer of why. Only and only when we are approaching the result. If we are not approaching the result, what I'm trying to say is that if we are not approaching the base condition we are having, there is no use of calling the function itself. So in recursion, what happens is that every time I'm calling a function, some I'm some bit forward to the base condition I am having. So every time I'll call the function, the main input of my function will decrease. So let's say I have started with n and I have to go till 1. So each at every call my n will decrease somehow. Let it be any proportion, if it is decreasing by 1 or 2 or 3 or whatever, but it should reach 1 at some particular time. So what I'll say is that recursion as a programming technique where we solve the problem by solving we will solve the complex problem by solving its smallest sub problems. Okay, so let's try to write out some code for the recursion. So while writing the code for the recursion, the very first thing, there are three steps. The very first thing is an assumption. This assumption is that whatever the function I am writing is correct. We have to first assume that the function I am writing is correct and it is working as we are expecting it to work. Secondly, the main logic. And thirdly, the base condition. These three, if we proceed in this way, writing out a recursion code will be very simple. So let's say I have to find the sum of n natural numbers. So what I will be having is some function int sum with n. So now, firstly, okay, so now how do we calculate the natural number of n? Can I say that the sum of first n natural numbers will be equal to n plus sum of first n minus 1 natural numbers. Can I say this thing? Guys, please reply. Can I say this thing that the sum of first n natural numbers will be equal to n plus sum of n minus 1 natural numbers? Okay, cool. So, similarly, the sum of n minus 1 natural numbers will be equal to n minus 1 plus sum of n minus 2 natural numbers, and proceeding further. So now what I'll do is to add n to the sum of n minus 1 numbers. That's what I'll do. So what I'll say is that return n plus sum of n minus 1 natural numbers. So right now what I am doing is that I am assuming that this sum function will give me the sum of n minus 1. I have not written anything, the base condition or the logic over here. What I am assuming is that this sum function will be returning me the sum of n minus 1 natural numbers. This is what I am assuming as of now for this particular case. So now when I am having a particular n minus 1 sum, what I'll do is to add just n over here and I'll get the sum of n natural numbers. So now what I'll say, now this was our assumption that the sum of n minus 1 will return me the sum of first n minus 1 natural numbers. Now this is our main logic, that we are adding this particular sum to the n. We are done with our assumption, we are done with our base logic, main condition. Now we will look into a base condition. What base condition is that the sum of one natural numbers is always 1, right? So if my n is equals to 1, I'll say return 1, and that's all. We are done with the assumption, we are done with the logic, the main logic, and we are also done with the base condition. That's all. This is a 2 line of code to find the sum of n natural numbers. Note it down. So similarly, we will try to find out the factorial of n numbers. So let's say I'm having a function in fact that is taking some int n. Again, so we will try to find out the formula from which I can deduce the factorial of n. What I'll say is that n factorial is equal to n multiplied by n minus 1 factorial. Is that correct? Okay, good. So what I'll do is somehow I'll assume that my function will return me the factorial of n minus 1 and I'll just multiply it by n. So what I'll do is return n multiplied by fact of n minus 1. Here I am assuming that this fact function is returning me the factorial of n minus 1 numbers. So now when I am having a factorial of n minus 1 numbers, I'll just multiply it by n and I'll get the factorial of n numbers. So this was our assumption. This both combined is our main logic. So now we'll come up to our base condition. What base condition is? It is same again as before, that if my n is 1, return 1. Because the factorial of 1 is 1. So let's try to write a code for Fibonacci series. Fibonacci series. Are you clear with these two, or if you have any questions, please ask. Good to go. Okay. So we will try to write out our code for Fibonacci series. Let's say I am at some nth number. My nth number will be counted by n minus 1 plus n minus 2. Correct? That's how Fibonacci series is generated. So now what I'll do is for any of the n input, I'll just find out n minus 1 and n minus 2 by assuming that the function I am writing is already returning me the value as expected. So what I'll say is that I have some function int fibo that is taking some int n. What I'll say is that for n, the value will be the sum of n minus 1 Fibonacci and n minus 2 Fibonacci. Return fibo of n minus 1 plus fibo of n minus 2. What I'm assuming is n minus 1. What I'm assuming is that this fibo function will return me the Fibonacci till n minus 1, and this fibo function will return me the Fibonacci till n minus 2. So now when I'll add both these two, I'll get the Fibonacci of n. Okay. So these two were our assumptions. This addition is our main logic. So now we will proceed to the base condition. So I'll say that if n is less than 2, return 1. So the Fibonacci series will be generated as like 1, 1, 2, 3, 5, 8 and so on. This 1 and 1 for the first n and for the second n. These both are 1. I'll say that if n, sorry, this is the 0th index and this is the first index. So what I'll say is that for n is less than 2, I'll return 1. And for any of the n, I'll just try to find out the n minus 1 and the n minus 2 and I will get the answer. Are you clear with this? Okay, so understanding this particular flow is really very important. I'll just repeat it again. While writing, if you will start with, okay, that there is no harm in writing a recursion code one by one. You can write out the base condition, then you can write out the main logic, and then you can use the smaller sub problem. There's no issue in writing that, but that is really very difficult, as while writing the base condition you don't know what you are going to call next. So how we proceed is that we first assume that the function I am writing is already giving me the output as it is expected. So while writing out the code for the smaller sum problem, you don't need to think that what it will return and what it will not. Just assume that yes, it will give you the result. Whatever the result you get by the smaller sub problem, apply the main logic on it. So in this particular case, we are adding the two last Fibonacci. Previously, we were multiplying. Previous to that, we were adding the sum of the natural numbers. So what I am doing is to call the assumed function. Then I am writing out the main logic, and then I am coming to the base condition. If you proceed in this way, you will never have to think what my base condition will be and what not. That will be very clear to you. Okay, so we'll proceed further. Yes, we were talking about those time and space complexities, right? We will again try to reduce the complexity for this for the examples we just wrote. So the first example we wrote was the sum of n natural numbers, that was like int sum, sorry, um, int sum that is taking some int n as input. What it was doing is to return the sum of n minus 1 factorials, sorry, n minus 1 numbers that was added with n, this particular value, where my base condition was n is 1. If n is equals to 1, return 1. So we will try to find out that for a particular n, how many times this sum function is called and how many number of iterations we are having. What will be the time complexity for this? So let's say, okay, so we are having some recurrence relations. Using the recurrence relations, we find out the complexity for a recursive approach. So let's say I give n as 1. It will come inside and I'll check that if n is 1, it will return 1. So this is a constant time operation for n is equals to 1. It is constant time. Let's say the time taken for 1 is 1 unit. It's constant, right? So what I'll say is that for t of n, what it is, this 1 plus the time complexity, the time taken by sum of n minus 1, what I'll say is 1 plus t of n minus 1. Are you clear with this relation? The time taken for n is equal to 1, a constant time, plus the time taken by n minus 1. Is this clear to you? Um, I think it's not clear, that's why you're not replying. Okay, I'll explain it again, no issues. Let's say, okay, what's the complexity of 1? If I'm giving 1 as input to this particular code, why I'm taking 1 into the consideration? Because 1 is our base condition. I'm trying to find out the complexity for the base condition. 1 is our base condition. So what's happening is that for n, if n is 1, I'm simply returning 1. So the time taken by t of 1 is 1. Now I'll try to find out the complexity of t of n. What is the complexity for a t of n? It will be equivalent to, let's say this is taking some x amount. This sum function that is called here is taking some x amount of time. What I'll say is that there is some constant operation added with x amount of time. I'll say 1 plus x. Now, what x is actually equal to? T of n minus 1, time taken by n minus 1 elements. I can say that it is 1 plus t of n minus 1. Is it clear to you now? Is it clear or not? Or should I repeat again? Okay, it's clear. Okay, cool. So now I am having t of n is 1 plus t of n minus 1. So what I'll try to deduce the time complexity of n minus 1. For reducing the complexity of t of n minus 1, I'll just insert n minus 1 over n here. So t of n minus 1 will be equal to 1 plus t of n minus 2. 1 plus t of n minus 2. Is that correct? try to think upon a bit that how it is reduced. For t of n, if it is taking 1 plus t of n minus 1, then for n minus 1, it will take 1 plus n minus 2. For n minus 2, it will take 1 plus n minus 3. That's how it is reducing, right? Yep. So now, I will substitute the value of t of n here for t of n. What I'll say is that I will place this value here. That's 1 plus t of n minus 2. That's 1 plus t of n minus 2. Got this? So now it is equal to t of 2 plus t of n minus 2. Got till here? So now I'll say what will be the value of t of n minus 2. That will be equal to 1 of t of n minus 3. I'll again substitute the value of t of n minus 2 over here. That's 2 plus 1 plus t of n minus 3. That's 3 plus t of n minus 3. So let's say I'm going till some k pointer, k of t of n minus k. You got till here? Okay, cool. So now what I'll do is, after I'm having some formula of t of n, that is in the form of k, that is k plus t n minus k. What I'll say is to substitute this n minus k with her base condition. What our base condition is? That's 1. So okay, why I am writing 1 over here? Sorry, just a second. T of 1 was 1, right? What I'll say is to substitute this base condition, whatever the base condition we got. In this case, it is 1. It can be n, it can be n square as well. So right now it's 1, right? So what I'll say is to substitute this particular value, n minus k as 1. So what will happen is the k will be equal to n minus 1 according to this. Cool. So now I'll replace the k over this point. I'll say is n minus 1, the value of k, plus t of n minus 1. So this is n minus 1 plus t of n minus n plus 1. That's 1. So the time taken by one element is the time taken by to calculate the natural number of one element is 1. We already reduced that. So it's n minus 1 plus 1. So the total complexity is O of n. You got this? You got this, or is there any confusion, or do you need some time to revise it? Okay, we will go to this thing again, so that will be better for you to digest. Okay, the first thing that we did is to find out the complexity for the base condition. Base condition over here is 1, n is equals to 1. So now what I'll say is that time taken for calculating one element is 1. It's just 1 unit of time. There is no loop or nothing. We are just returning 1. That's a constant time operation. So what I'm saying is that for n elements, it will take 1 plus time taken by n minus 1 elements. That's how we came here. Now we will substitute the value of n minus 1. It will come up to 2 plus t of n minus 2. We will substitute the value of n minus 2. We'll say it is 3 plus t of n minus 3. So now there is some pattern over here. 1 plus t of n minus 1, 2 plus t of n minus 2, 3 plus t of n minus 3. So I can write it in the form of k, where k plus t of n minus k. Now, whatever the value we are having inside n minus k, I will replace it this with this one. This is the time taken by our base condition. So now I have to get the value of k over k from here. K is n minus 1, will transfer a n over here and here. So that will be k of n, k is equals to n minus 1. We will substitute this particular value in this particular equation. So k is n minus 1 and the time is n minus the value of k is n minus 1. So n minus 1 plus this will cancel out to 1. Now t of 1, we already know the particular value of t of 1. It is 1. So here we were having n minus 1. These 1 and 1 will cancel out. What we are left with is n. So this is our time complexity, that the time taken is linear. You got this now? So this is what we substitute. Okay. Why we have put t of n minus k? You are asking for this of t of n. You are asking for this. Okay. So this is what we have to substitute. Whatever the t value you are getting, you have to substitute it with the base condition. This is a procedure. Okay. Good. Okay. So we'll proceed further. Okay. So you will be able to write down the complexity for um, what the second question will be? Factorial. Will you be able to write down the complexity for factorial? That's very similar to what we did just now. So in the case of factorial, again the t of 1 will be 1. Here, here again it will be 1 into this particular thing. That will be 1 multiplied by t of n minus 1. And again, this what all the difference will be of this plus and multiply. Try to reduce it on your own. If you are not able to ping me, I'll let you know how do you reduce. So we'll come to Fibonacci. That was having two smaller sub problems that we have to face. So the code was like there is some int Fibo. of some integer, what I was doing is to return the value of summation of fibbo n minus 1 plus fibbo n minus 2. Let's say if n is equals to 1, return 1. Okay, so now again the time taken for one element is 1, as it is the same. We have to find out t of n. What I'll say is that it is calculating n minus 1 element, the complexity for this, and for the complexity for n minus 2. I mean, the time taken for n minus 1 element added to time taken to n minus 2 elements. What I'll say is 1 plus t of n minus 1 plus t of n minus 2. This will be my relation for t of n. Are you all clear with this? Are you clear with this? That t of n is equals to 1 plus t of n minus 1 plus t of n minus 2. That's how we are calculating, right? This fibbo is t of n minus 1. This fibbo of n minus 2 is taking t of n minus 2 elements. Are you clear with this relation? Um, Guys, please respond. If you are not, I'll explain it again. Okay. So now, what? Okay. Previously we did it. This was a recurrence relation. This is the this is one way of calculating the recurrence complexity complexity for recursive code. This time, let's say we are not going for the recurrence relation. We are going for the recurrence tree. There are two ways to find out the complexity. I will do this by recurrence tree, so you will be able to get to know both. So for t of n, it's 1, t of n minus 1, and t of n minus 2. These all are the calls. Again, for t of n minus 1, it's 1, t of n minus 2, t of n minus 3. For t of n, it is t of n minus 3, t of n minus 4. So in here, the time complexity was 1. I mean, we are just trying to find out the total complexity. For this thing, calculating is 1. For calculating this level, the whole level is 2. Calculating this whole level is 4. Okay, maybe you got it or not. Let's say this is 1, right? This is having 2 calls. That's why it is some 2 unit of times. Again, this is having 4 calls, right? This particular level. That's why it is 4. So now t of n will call 2, this will call 2, this will call 2, this will call 2. So the next level will be 8. Similarly going, it will go in this particular fashion. Are you clear with this, why I have written these particular values over here? Okay, so let's say I'll draw it again, no issues. T of n, I am having 3 calls. Are you clear till here that t of n is having 3 calls? That is for 1, for n minus 1, and for n minus 2. Okay, cool. So this right now, calculating this is a constant time operation because it is not having anything related on this particular level for this particular first level. Now we come to the second level. We come to the second level. Calculating the second level, I'm not talking about the complexity for t of n minus 1 or n minus 2. I'm trying to deduce that for the second level, how many calls are there? The number of calls is t of n minus 1, t of n minus 2. That is 2. Now for the third level, this will call three things. One will be 1 and 2 function calls. This will again call 1 and 2 function calls. So how many number of function call is there? 4 for the third level. Proceeding further, it's 8, it's 16 because every time it will be multiplied by 2, right? So let's suppose for some nth row, this will be the number of calls we are having. That's a 2 power n series, right? So this will be the uh, number of calls at some particular nth level. Are you all clear with this? Why I have written 2 power n? Sorry, my bad. That's the zeroth level. That's the first level. That is the second level. Are you clear with why I have written 2 power n? Please respond. If you are not, I'll do it again. Okay. So now the total complexity will be equal to the sum of this for the time taken by zeroth level, the time taken by first level, second level. The total complexity will be equal to the sum of all of these elements. So now 1 plus 2, the sum of 2 power n series for n elements, it is always equal to 2 power n plus 1. This is the formula. You can deduce it also. So now what I'll say is that my total complexity is O of 2 power n plus 1. Again, we will remove out the constants we are having. So we will remove this plus 1 and I'll say that the complexity is 2 power n. Are you clear with the complexity here? Are you clear with the complexity or should I repeat the everything again? Others, please respond. Repeat it. Okay, cool. So now I'll try to write it again. My t of n was 1 plus t of n minus 1 plus t of n minus 2. Correct? So I'll draw the recurrence t for this. This is my zeroth level. This t of n is calling 1. That's calling t of n minus 1. That's calling t of n minus 2. Correct? Now this n minus 1 is again calling 3 times. That's 1. That's t of n minus 2. That's t of n minus 3. Now again this will call 1. This will call n minus 3. And this will call n minus 4. Are you clear till here? Okay. So let's say it was my zeroth level. The number of function call is 1. In here, in this particular level, the number of function call is 2. In here, the number of function call is 4. So now every time it will be multiplied by 2. In here it's 8, that's 16 for the next levels. So let's say for my nth level, the number of calls will be 2 power n, because that's a 2 power n series we are coming. 1, 2, 4, 8, 16, 32, that's a 2 power n series. So now the total complexity will be equal to the sum of all these elements. We have to calculate this 0th level, first level, second level. So the combined complexity for this will be the total complexity of my code. So now the formula for the summation of 2 power n series for any of the n is 2 power n plus 1. That's the formula. You can try, you can also add it and you will also get this particular amount. So now what I'll say is for any of n, any of the n provided, my complexity is O of 2 power n plus 1. So now we know that we have to remove every of the constants we have. Plus 1 is a constant and I'll remove it. So what I'll say is that my total complexity is of 2 power n. Are you clear now? Okay, cool. Cool. So we discussed some recurrence relations and some recurrence tree. Recurrence tree is really very simple. You have to just count the number of function calls in a particular level and add them up. Recurrence relation, you have to practice it a bit. Without practicing, you'll not get it. So I'll give you some practice questions over here. T of n is, let's say my function is 2 of n by 2 plus n. This is my one recurrence relation. My second recurrence relation is some t of n is equals to 2t of n by 2 plus 1. Let's say t of n is equals to t of n by 2 plus n, and t of n is t of n by 2 plus 1. So this is your homework. You have to find out the complexities for any of the given code whose particular t of n, the recurrence relation is this. Okay, we will discuss it in the class as well, no issues. So as of now we will take a break. We will resume the session after some time, maybe some 15-20 minutes. Till then, take a break and try to think about take any one and at least try to find out the complexity for at least one of them. Okay. Is that okay? Are you clear with your homework? Okay, so we will close the session for now, and I'll send you the link for the next session. So